Should we start?
Yeah, sure.
Okay. So welcome everyone to the Grothendix School of Thoughts. Today is the second lecture on the K theory and G theory of schemes, and today's speaker is Dr. Rahul Gupta, and he will talk about localization of K theory for today. So please carry on.
Yeah, thank you. So, okay, so again, this lecture also, like last one, will not be a self-sufficient lecture, but it's about the giving the ideas and main important things about algebraic G theory and algebraic K theory. Okay, so let's recall what we did last time. All that we defined G groups and K groups for a scheme X. By scheme, recall that we always took Noetherian, quasi-separated. Sorry, separated. Scheme with an alpha. So many things do make sense for general schemes, but we will restrict ourselves to this class. Scheme X. Okay. What we saw last time was that K theory is contravariant. So for morphism f from X to Y. First, we always have pullback along for K groups. We have push forwards for G groups. If that is proper. And third was, we do have pullbacks for G groups when so f is of finite odd dimension, and in particular f is flat. So I will just say flat. Okay. So yeah, the functionalities which we saw last time with some relation between them. The fourth thing we talked about was duality, that the canonical map, the natural map. There's a natural map from K groups to G groups. It's an isomorphism. Isomorphism. 。 When X is regular. If it's a regular scheme, then there's no difference between G theory and K theory. So obviously we have two theories and we always want to see which theory is nicest one. And the point is, many properties of G theories are nice, which we'll talk about today, localization in particular, but it has in some sense, a bad property, I would say. That is what we saw last time, nil invariance. What is that? It says that GI X reduced, happy to say GI of Z, GI of X, isomorphisms. Ideal of Z is important. So in particular, there is no difference between G theory of a point and a thickened point, and which is not nice, I would say, because we want to differentiate between these two schemes: the scheme given by a point or given by a thickened point, a double point. And this says that K theory should be some invariant which we should understand. Okay, so this is I would say it's nice to work with this kind of statement, this kind of nil invariance, which is coming from a research, but it's not. It makes G theory very weak invariant, I would say. Okay, so this is what we did last time. So today we'll start with a nice property of G theory, which is localization. What G theory? Okay, bear with me. Okay, so let me state the theorem, and yeah, then we will pause a minute and see. So let Z be a closed scheme. And let U be a complement of Z in X. Okay. Then what localization theorem says that how to relate the G theory of X with G theory of U and G theory of Z. There are obviously this pullback and push forward are there. We call that J is open immersion, so it's flat, so there is a pullback on G theory. I is closed immersion, it's proper, so there is a push forward for that. For I, right? These two maps are there, but it says that these two maps fit into a long Z sequence. Gi minus 1 of Z, so on and so forth. G naught of Z to G naught of U, G naught of X to G naught of U. Yeah. So this term says that there is a long Z sequence with G theory of Z, G theory of X, and G theory of U. Okay. Is the statement clear?
Yeah.
So it's very nice statement about some invariant that we can understand G theory of X if we know from U and Z basically. So that's the idea. Let's see a proof of this. Obviously, not complete proof, but sketch of the proof. So the main idea why we work with the G theory and we cannot work with the K theory in some sense is that we apply pull-ins, we apply pull-ins, localization, theorem. What are very so he said there are some abstract localization theorem for K groups of abelian categories, not exact categories. Okay, so what does it state? Let me write this abstract statement, state localization theorem, and then we'll see how to apply this. Okay, so yeah, let me write it. That is, if A is an abelian category and B is a full subcategory of A, is a full subcategory such that it is closed under subobjects, subquotients. This makes it abelian category, and we require closing the extensions also. Okay. such subcategories we call as shared subcategory. It is satisfied, it is closed in a sub-object, sub-quotient, and not sub-quotients, quotients. So objects, quotient, objects, and extensions, that is called shared subcategory. So if I've given a abelian category and a shared subcategory of abelian category, which is a built category in turn, then we can talk about the quotient subcategory. Quotient category is an abelian category. Abelian category such that the following is a long sequence. Is exact. Okay. So basically, what we have is that A theory of A over B, A theory of B, A theory of A, and so on. Yeah, it's a long sequence. Is it okay? Statement is clear? So what do we have? We have an abelian category A. We need, obviously it's about G theory. So we are working still with the abelian category. So there's abelian subcategory of A basically, which we are saying that it's closed under all sub objects and subquotients and extensions as well. Then we can talk about the quotient subcategory, quotient category, which is also abelian. We can talk about K theories of them, and they will fit into our long exact sequence. Okay. So we have to apply this basically. Is the statement clear? So we have to find out categories B and A such that, so the task is to find A, B, such that the K theory of A is just K theory of X, K theory of B, right? It's a, yeah, so B maps to A and A maps to this. So Z, X, and U. So K theory of Z and K. This quotient category should be K theory of, sorry, so G theory. Please let me not make these mistakes. Okay. G theory. Is the statement clear? What I'm trying to say here? Is it okay?
Yes.
Someone? Yeah. So we have to find such categories. So this immediately tells us what my A should be. A should be M of X. Yeah, should be all quasi-coherent, coherent OX modules. Category of coherent OX modules. So what my B should be, so that A mod B is equal to MU. That's the question. So take the subcategory objects. There's a subcategory. Okay? So I'm just going to tell you the objects. Such that support of F is contained inside. Is this statement clear? So what you're demanding is that, so which is equivalent to say that, that is equivalent to say that J pullback of F is 0. Okay. So we are saying that we take all those OX modules whose support is contained inside the closed subset, which is supported by this closed subscape. Is it okay? This B just depend on the closed subset X minus U. Not any scheme structure is not there. Okay.
Yes.
Good. So now basically, so the first first claim is that, so enough to show, so let me write enough to show these two claims. First claim is that K theory of this B is actually G theory of X, J theory of Z. Is this, do we know how to show this? Anyone? So this follows from depreciation. This is what we saw last time. Okay. So basically, it says that G theory does not see any stable structure on Z. You take a linear structure, put any other structure, you take any other ideal shape whose zeros is just this closed subset X minus U, G theories are going to be same. And they are going to be same as this, the K theory of this exactly B. That's the content of this Trivias theorem which we saw last time. Okay. So this is done. So this was enough to show, and we have shown this basically. I'm clicking here. Okay. Is it clear? Let me write it down because no one is responding. Which that follows. Okay, so this first step is clear. Second step we have to show is that it's enough to show that this quotient category is equivalent, maps and equivalent to category of OU modules. Right? If I show this, then we are done. Because then this step will be true. Yeah? Okay.
Yes.
So we have to just show this. So this follows. This follows. That this map mx to mu is essentially such. This exact functor is essentially such. Do you remember such statements from your algebra geometry course? This was an exercise in Harshon. Let me code it. Exercise. Harshon, second chapter, section 5. Exercise. 5. Okay. So the exercise says OU modules can be extended to an OX module, coherent OX module. Any coherent OU module can be extended to a coherent OX module. May not be unique. Obviously, it's not going to be unique. But the point is that that's why we have to kill these things basically where whose pullback to U is. Right? We have to kill all those coherents. Okay? So this finishes the proof of localization. Any question on this? Yeah, is it clear or should I explain a bit more? Okay.
No, it's fine.
Yeah, how is this isomorphism holds? Basically holds formed by the uniqueness property, this universal property of this quotient. And what we saw is that A maps surgically to this, essentially surgically to this mu, and then we have to show that this category basically has this property that so this is the abelian, this is a universal category map, universal abelian category, initial abelian category, initial in the class of abelian categories which get a map from A and which kills the objects of B. But this category does that. That one has to verify, and that's an easy check. Okay, but this is the main step basically. Okay, good. So we have proven this localization for G theory, which is easy to prove given the localization on abelian categories. Let us discuss some applications. Why it was so important to have such a strong result. So first application I will talk about is homotopy invariance. and I write this property as HL. So what's the theorem? Let F from E to X be a vector bundle on X, then pullback map. See, vector bundle, which means it's a flat morphism. So we can pull back G theories. J of X to Gi of E. Okay. So we are saying that there is no difference between X and vector bundles also. So we saw that the nil invariance was saying that there is no difference between X, Z, X reduced and X. But this is something which we want also, right? Because the prime, so we kind of want this kind of a statement from our invariants because note that this implies that theorem implies that G theory of X same thing as G theory of X cross A. Yeah. So which means that ANs, these affine spaces, do not have any G theory. Is not you can just look at a point, but on any X it happens. Okay. Is it okay? The statement is clear? Yeah. Okay. So in your in this lecture series on K theory of rings, you guys have seen that G theory of a ring in this pullback map, G theory of RT is an isomorphism. Yeah. So we know that the G theory of R and polynomial rings over R, they are same. This is a statement which we just talked about. Not even a proof, I would say, but yeah, I guess he did say this. So we are going to assume this and then try to prove it for general X. Is it okay? Okay, so let's see. So in particular, so this implies in particular we have that. All affine schemes. Okay, so let me write it down because so GI X is an isomorphism to GI of X cross AN. X is active. Yeah, because here we saw that it is just A1, but then I can take A1 one more variable on this RT that will be also an isomorphism and so on and so forth. So we can induct on this end. Okay. So we said, okay, so if my X, so in this theorem, if my X is affine and my vector bundle is trivial vector bundle, then I know the isomorphism from the G theory of rings, whatever we did in the G theory of rings. Okay. And we want to conclude it for scheme and general vector bundle. Okay. So to conclude it for general scheme, schemes we use Noetherian induction. So we are assuming our scheme to Noetherian and we are doing that is okay. So in particular, we assume. So we first assume that the theorem is true. It's true for all proper proofs. Subscripts. Proper closing schemes of X. Yeah, which means that if I take a proper closing scheme of X, say Z, take a vector bundle over that, my G theories are not going to change. Okay, and to show HI, what the weight varies for. So this is what we have to show. Okay, so what we have G theory of X. I want to compare it with the G theory of. To do this, let U inside X a fine open subset such that E restricted to U is trivial. Yeah, we can always achieve this kind. We can always find such a U which is not non-empty. Yeah, so obviously this is non-empty open set. Okay, is it okay? We can always find such a U so that EU is trivial, and we can assume further that it's Fi. Okay, so then we use this open set and let Z equal to X minus. So I'm going to fill this on the top diagram. So I have G theory of U, Gi minus 1 of Z, Gi of Ge restricted to U, I minus 1 of E restricted to Z. Yeah. Similarly here, Gi of E restricted to Z, Gi of Z, and so on and so forth. Okay. Note that. Ez is closed subscheme of E such that EU E to U is just E minus E to Z. Right? And all these are vector bundles. So this is vector bundle over Z, this is vector bundle over X, and this is a vector bundle over. My U is affine. So by our previous step, we know that this is actually an isomorphism. This we know by our affine case. Affine and vector bundle being trivial. So this is the case which we just talked about in the top, this case. So it's an isomorphism there. By Noetherian induction, we know this is actually an isomorphism. This is actually an isomorphism. And obviously there's a term I should write here. G I plus 1 of U. G I plus 1 of E restricted to U. This is also an isomorphism. In particular, get this answer, right? By 5 lemma. We conclude by 5 lemma and diagram is done. Conclude the proof. 5 lemma. Okay. So basically, it says that if you know something locally and the structure is preserved under these pullbacks and to closed and open sets, then on G theory you know it for global things. Okay. Any comments?
Can you move to the above diagram?
Yeah.
Yeah, here this connecting map GI plus 1 u to GIZ, that's coming from the long exact sequence of the previous theorem.
Right. So these maps are there. And yeah, you're right that one has to say that all these long exact sequences are actually natural. Yeah. What does it mean? That these diagram commutes. One has to prove that. There's a part of the localization theorem which I have not stated, but these long exact sequences are actually natural. Is it okay?
Okay.
Yeah. So obviously, this is when you write, I should write x u here or x z here in this boundary, and here I should write e and e x to z or something, e to z or something. But the point of naturality is that these are just boundary and these commutes. Okay. Yeah. Otherwise, location theorem will be useless if it is not natural. Yeah. So it's natural in the flat morphisms right now, or whenever there is a pullback actually. Okay. Good. So this was the first application of localization theorem, that we can prove commutative invariance if we assume the commutative invariance for affine things and trivial vector bundles. Let us look at the other application, which I guess all of you must have seen at some point of time, which is May vectors. So what May vectors say? It says that sorry, no, I'm calling everything as 3-1. Okay. Let U and V be two open subsets of surface Tmax, then there exists a long exact sequence U X. Go back to intersection coming from union. So these are national maps, pullback maps, and they are boundary maps. So let me G. So, and so on. Okay. Is it okay? So have you seen this look how to conclude the May trace from localization theorem? Have you guys seen this such a proof? No? Let me try to give a proof. Let without loss. That's equal to U. We just need U and V. So we can assume that and let y equal to x minus u. So we obviously have two open sets and two subsets, so we get longer sequence. So we drag some two longer sequence, I will still get a longer sequence. Is that longer sequence? And by sum, I can go from here to gi of x, and I will write a longer sequence of disjoint union of. So one can see since so. Then, because u and v, union of u and v is equal to x, my y and z have trivial intersection. Yeah? The union in x is actually a disjoint union. So this makes sense. It's a closed scheme of x. Okay. And obviously, there's a map, closed immersions, which is isomorphism, and yeah. And again, this map is gi minus 1 of y and z, and gi minus of y disjoint union z. This is also an isomorphism. So this is there, and now a diagram changes. Okay. Okay. Is it okay? So I would suggest like try to conclude this long sequence from this diagram. It's a fun exercise to get this map also, this boundary. So all these things are known to you. This is pullback, this is pullback. You have to see that this is exact at this point. But then one has to construct this boundary also, which is fun to do from this diagram. Okay, I will suggest everyone to do that if you have not already seen this. So we move on, and now we want to focus on my all things I wanted to say about G theory. So we saw that there is a nil invariance, there's a very good localization sequence which connects Z, X, and U, G theories of Z, X, and U, and which implies homotopy invariance for G theory for all X, for all schemes, and gives some their victories also in the nicest way. So input, so we now want to focus on K theory, K basically. K groups. Note that. So that we get homotopy invariance and May victories for K theory of regular schemes. Yeah. So I want to pause it here a bit because you will see that obviously this is because of duality. Huh? Yeah. So I want to pause here a bit because I want to. Yeah. So why do I focus on this kind of thing that I have homotopy invariance and big victories for regular sequence on K for K theory? The point is that obviously this is obvious now when we talk about G theory, but both these statements actually make sense for K theory for any scheme, in particular for regular schemes. We can talk about homotopy invariance. We want to ask whether K theory of X is same thing as K theory of X cross A1 or a vector bundle over K over X for say for X regular, because we know that regular schemes or smooth schemes for that matter, smooth cost projective schemes of some field, they're nice category. That is, those are nice schemes. We want to ask this kind of question whether they are it's a K theory is homotopy invariant for regular schemes, or does it have May victories kind of statement for regular schemes? You see, you can't. So what I want to emphasize is that to prove this homotopy invariance or May victories for regular scheme, you can't remain in the world of K theory. You have to go to G theory. You have to use this mx basically, right? Because somehow some complements get involved, some x. So if x is regular, open sets are regular, obviously, but its complement may not be regular. It might be very similar. A very reduced structure on your complement might be very different. Okay. So then you don't know anything how to play. So even if these two statements has nothing to do with the complements, if they are just about regular schemes, somehow when you try to prove it the way we prove them, it is required much more than that. Much more than we have to go beyond the beyond the category of regular schemes, and in particular we have to consider G theory. We have to look at K theory as G theory to conclude these things. Okay, is this remark clear? Is it okay?
Your remark is only for regular scheme.
Yeah, the point is like, because K theory of regular scheme is same as G theory of regular schemes. So homotopy invariance and wave vectors will hold for K theory of regular schemes. My remark is just to emphasize that even to prove these two things, homotopy invariance and wave vectors, which makes sense for K theory of regular schemes, you have to go beyond regular schemes, and in particular beyond K theory. You have to consider G. And we want to understand now. So basically, we are saying that all we kind of know the things which we want to know for K theory of regular schemes, but we want to see what happens for non-regular schemes. Yeah. So in general, let me now point out. In general, homotopy invariance is not true. Okay. So for singular schemes, actually does not have homotopy invariance. So singular schemes cross A1 can have some K theory, other than the K theory of the schemes. What about? The question is, what about localization first? Maybe we will see, it will follow once we answer this question. Localization. And what kind of localization we want to talk about. So this is my remaining half the talk. We'll be focusing on this localization of K theory. And this is much more important. Okay. So observation one. So what are the obstructions to when we try to address K theory of localization? So recall that for localization theorem for G groups, G theory, we used that the canonical pullback map from MX to MU is essentially surjective. But it is actually known that for singular schemes, K theory of X, K theory of U, the pullback map, the map is not always surjective. So there are counterexamples. Yeah, so we definitely can't expect Px to Pu map to be essentially surjective because Kx to Ku is not, cannot is a class S, and even then it's not surjective. So we can definitely not assume Px to Pu map is surjective. And this is one of the main obstructions. So what people started doing? So as I said, always that mathematicians do not stop. So this is not true, but what one expect is one can expect that the projective modules, so that if, let me write in the words in this mathematics, if I take a vector bundle over U such that its class, so as a class in K0 is 0, it's trivial, This is same thing as saying that P is, that is if and only if, for the one thing, P is stably free. Stably free. If you don't know, just think is a some invariant. If it is 0, then we should expect that then P extends to the element of Px. What extend means? It just means that they exist. That is, there exists some vector bond over X such that P prime distributed to U is P. Okay, so one can expect such a thing. That was that's the next solution which we would like to have. If my projective module has class 0 in K naught of U, then I should be able to extend it, because I know that if these non-trivial classes, they are non-trivial classes which are not extending to K naught of X. Right? So this map is not surjective, so we should expect that 0 element should be kind of have. Yeah. Okay, but unfortunately, Sayre proved that even this is not true. This is not true. Okay, so which means that so Coulom's method don't have any hope to give a localization. Theorem for cubes. Okay, is it state? Am I clear here? So his point is that this nicest property which we had for all these abelian categories actually is not true when we go to the exact categories Px and Pu, and is a big failure. And people were trying and they were saying that okay, we know that this map is not surjective, but maybe this surjectivity is the only obstruction to get a this long sequence. And for that, people guess that okay, if this kind of statement is true, that all projective modules, vector bundles over U, which have trivial class in K naught of U, if they extend, then there was a hope, but say like give a counterexample so that it's not true. So this started basically it was a big headache but for Thomson, and if you read his book, Trobo helped him in some way even after his death. So Thomson and Trobo which I will call TTN. Worked with. Okay, so okay, let me just say this. Work with the category of perfect complexes. And used Waldhausen's idea a theory. This idea to resolve the problem. Yeah, we'll see how they did it in a moment. So point was they were looking for the localization, and the kind of the obstruction was that this category of projective modules, it is too rigid. There is no room of, there is no freedom to move basically. So what the thought is that it's better to work with a derived version of that. Yeah, you have to take a complex set of, say, vector bundles. That was the basic idea, that we should look at the derived categories instead of this categories, this exact categories. And during that time, they had Grothendieck idea, like Grothendieck cannot of a derived category, but no idea of how to define higher categories of a derived category of perfect complexes or anything. And then Bolhausen defined what we know as Bolhausen categories and K3 of them, and they used it to define K3 of scheme in a much more general way, which agrees with current K theory for nice schemes which we are taking today. And then they could prove a lot of properties. The collections they proved, and from there they can do a lot of applications. So we'll talk about some of them, but not too many. Okay. So this is the back story, which I find very fascinating. Why we have to go to the Bolhausen categories? Because someone like me who just work with the K theory, it's not like I won't want to go read some abstract category theory and K theory of abstract category unless it's really needed. And this says that it is actually very, very much needed. Okay. So let me define what is a perfect complex. Is it okay? Any comments or any question? Should I continue?
Yeah.
Okay. So as I said, so the idea was to so we will work with the complexes now. A complex A of OX modules is said to be perfect complex or a perfect complex if it is quasi-isomorphic complex okay. So I will complete this. It's not complete. So okay, why we do work with vector bundles or projective modules in terms of. So my point of view is like obviously we are interested in C modules or trivial bundles, and somehow they do not matter. Yeah, so if something is locally trivial, it may not be globally trivial. Are projective modules, and they like we want to work with something. Hello. Okay. Yeah. Good. If locally, we have to write locally. Quasi-isomorphic to a bounded complex of vector bundles. Is it okay? So this I was just trying to justify why we have to require this local condition. Like I should be able to find a cover of X such that if I restrict my complex to that cover, any open set from that cover, it should be quasi on that open set should be quasi isomorphic to a bounded complex of vector bundles. And local condition is very much needed to develop any theory. Okay. Is the definition clear?
Yes.
Should we spend more time? Like it's just some complex which may be unbounded by itself, but you're just demanding that okay, locally should be quasi-isomorphic to a bounded complex. That's all. It can be unbounded by itself, but locally it should be bounded. It should be quasi-isomorphic. It means it should not have homologies only but finitely up to, yeah, it should have only but finitely many non-zero homologies, and yeah, there should be multiple ones. Okay. So obviously we have to construct a Ward-Husson category out of this. So what's the Ward-Husson category? So yeah, so I will denote this category that let's denote the category of perfect complexes with the morphism of complexes, the subcategory of complexes of Quest models. Okay, and then we want to define Ward-Husson cofibrations and leaky cleans from this. So let me write this word. I'm not going to discuss them, but I want to be taking the note. Spatial by Ward-Husson category. Perfect complexes. With fibrations, so cofibrations. X split monomorphisms and weak equivalences as classes. Okay. So if I take cofibration as split monomorphisms and weak equivalence as quasi-isomorphisms, it becomes a co-simplicial Ward-Husson category. And then there's a dual also. You take the quotients to be split epimorphisms. It becomes a co-simplicial by Ward-Husson category. And definition is, yeah, so that theorem, definition, I will define the joint Thompson and Schubach K theory of X to be K groups of this Ward-Husson. You guys have seen the this K theory of Ward-Husson categories, right? Okay, so I'm not going to discuss a lot of structures on that and anything. So it's good that most of you must have seen, or just take that there's some like exact categories. They have some structures for other categories. There's a S construction, like Q construction, exact categories, and then you can take again the same thing. Take the loop is take the classifying space, loop space, and then realization. Okay, so you get a topological space, which is an infinite loop space, and you take the pi i's of that.
I have a question.
Yeah.
The notion of map between two perfect complexes is the usual map of complexes, right?
Yeah, it's a usual
No.
complexes.
Okay.
Okay. So yeah, this is a definition which I am taking from myself because we are working with noetherian schemes. Okay. So when you work with a general schemes, you have to take some other conditions here in this definition of course. Yes, but I'm not going to discuss. I'm not going to say anything about that. So theorem is that for our scheme. So this is our scheme. Okay. Like noetherian and separated and having this line bundle, variable line bundle. Scheme, the theory of X, which we are working is with the theory is actually isomorphism. Yeah. So what we are saying that this is a different view of looking at our K theory. So we define the Klein K theory by some exact category, K theory of exact category, and you can do the same thing with the K theory of a Ward-Husson category, and they are turn out the same for nice X. Is it okay? So we are not doing something weird, basically. So okay, so by this theorem we will ask like why to be clear then about this what are the categories. Okay, and one of the very first thing is by the definition, which we can define in this Waldhausen structure. So U in X open and say Y is complement of X in U in X. Then we want to define what is the K theory of X on Y. So this is kind of thing which we are doing with the G theory, that it should be perfect complexes with support on Y. That's the concept here, and that's how you should think. For G theory, it was exactly the coherent sheaves with support on Y, which has turns out to be that the G theory will be same thing as G theory of Y itself. But here, what we are doing is that we are testing the K theory of some Waldhausen category, where this category is full subcategory of objects complexes. Okay, such that full back of is quasi-isomorphic to 0. Yeah. So up to quasi-isomorphism, we are saying that okay, it is supported on Y basically. Right? So yeah, that's the point. Okay, point is like when you are going to perfect complex, we are working in the derived setting. So we should look at all the identities which we are doing for G theory. We should look at them as a quasi-isomorphisms now, because they are complexes and the correct notion of equality is quasi-isomorphism. Right? And that's what we are doing basically. This is our WN, and there's a again weak equivalences and cofibrations are given by strict. So it's a subcomplex of perfect complex of X. Okay, so it inherits obvious cofibrations and weak equivalences. So that is a Waldhausen category. Okay. So with this definition, let me state a localization theorem. Theorem. So let close subset because it doesn't matter actually. Yeah. So this is, you can see that the scheme instruction on Y doesn't matter on this, just on U matters, which is correct, right? Because the localization should be X comma U. So it should be some exact sequence given by open set of X. So it should not depend on the stream structure of the complement. The same thing happening with G theory by the research, but here we are just taking it to the definition for us. Okay. Then there exists long sequence. Looks like we have to start with ki of X on Y now. Ki of X, ki of Y, so on and so forth. Ki not of X, Y. So the last map is not surgeon, which we said also, right? We do not expect this map to surgeon. Is it okay? You're saying that up to this failure of this map being surjective, we do have localization sequence. We can actually fill up, but this is just K theory of Pullen K theory you can think of. Because we are working the nice schemes, this is just a Pullen K theory. But here this something different come, which is not dealt with by the Pullen. It was coming from by this construction of Waldhausen categories. And they are complex about K theory in some sense. And we are saying that if we define like these groups, the way we define, we do get actually long exact sequence. Okay, is that statement clear? Is it okay? Do you want to prove this? Do you want to assume this and move forward? Up to you guys. Okay, so let me try to say some few words about the proof, and then we'll go to the application because we have 25 minutes roughly. Okay, proof with start. It's not a complete proof. So as we saw that when we were proving the G theory of localization for G theory, we saw that there was an abstract localization theorem, which was giving us long exact sequence, and we just applied that in our case with the correct categories, and we got our exact sequence. So that we will try to do the same thing here. So we need some kind of localization theorem for bordering categories, and there is such a thing. Localization for word. So let's talk about this. So what is the statement? That this curly A be a category with cofibers. So I have described the cofibers to start with. Cofibrations are fixed. And then we have two weak equivalences. The weak equivalences. It's my bad. Put some curly thing. One. Let AW, the full subcategory of objects of A such that 0 to A is now weak equivalence of by this W. Okay, so these are W acyclic objects. Under this weak equivalence, we will see how to apply it, and then it will be very clear what we're talking about. But they are very saying that there is a cofibrations, there are two set of weak equivalences, and we are taking the acyclic objects with respect to one weak equivalence, which is larger. Okay, and we will give the cofibrations on this AW to be just AW intersection with the weak equivalences in A. Sorry, cofibrations in A. Just receive the cofibrations, and weak equivalences we will give by V basically. We still want to invert these weak equivalences, which coming from V. Is it okay? Yeah. We now get three categories, and then we are saying that, yeah, that AI so on and so forth. This takes a long sequence. Yeah, so here we are saying that even K0 is also actually surjective. Here there is no problem. It's a very long, it's a long exact sequence. It has all the properties. It does not stop. Okay. Fine. So now we have to give you what is my WA, what is my VA, and what my AW looks like. Okay. So let's try to do that. So we take, obviously A will be our perf A, with our usual notion of weak equivalences. So we'll do W only here. Okay, these are usual notion. Let me not do that. This we want to explicitly talk about. Okay, so this is perfect with the usual cofibration. Cofibrations are just in split monomorphisms. And we will now discuss two equivalences. We will discuss two equivalences. Yeah, I would love you guys to guess, but let me not go there. So first is just, you know, this should be the K theory of X basically. So we will take here weak equivalence quasi-isomorphism on X. What we'll do here is that we'll take quasi-isomorphism weak equivalence to be quasi-isomorphisms after pulling back to okay. Is it clear? So what we are saying that in WA, the weak equivalences are, so a map is called weak equivalence if after pulling back to U it's in quasi-isomorphism. And here in VA, we are just saying that weak equivalence are quasi-isomorphism. So obviously anything which is a quasi-isomorphism on U itself is a quasi-isomorphism on on X itself is a quasi-isomorphism on U. Is it clear? Yeah. And now you see that if I take V of W, it's just the perfect complexes of A on Y. These are the exact perfect complexes which was pulled back to U. So these are exactly those X, those, yeah, I can, those A in X such that pullback of A is quasi-isomorphic to 0. Yeah, these are the things which are W acyclic. So W means this. So it fits into the picture. So now what we got is that K theory of AW, in particular K theory of AW is just K theory of X on Y. K theory of P of A is just K theory of X. So now it's enough to show that so let me call this K theory. So just let me say this that Ki of X for U by definition it's a K theory of basically W of A. Okay. So what is this? So let me just recall it. What we are doing is that what is this for means? For means that it's a K theory of perfect complexes on X with the V equivalence. Cofibrations are same as split monomorphisms, but V equivalences are quasi-isomorphisms on U. Yeah, they are quasi-isomorphism after pulling back to U. And enough to show. So these three things fit into a long exact sequence. That's what we saw by the abstract localization theorem for what are the categories. So it's enough to show that K theory of U mapping to the K theory of X. So that's the other way around. K theory of X for U, which means this K theory, mapping to the K theory of U after pulling back. It obviously maps this Gaussian category to perfect on U. Maps to this. take the weak equivalence to weak equivalence and covibrations to covibrations, is an ISO for I greater than equal to 1 and injective for I equal to 0. Yeah, this tells you the picture also. The entire picture basically tells like, so this is not the kind of correct thing to do when you want to understand K theory of U. It should be this K theory to give the long exact sequence, which means the trajectory on K naught as well. But we're actually interested in this K naught Ki of U, so we compromise there basically. Is it okay? And this is a hard step, and it's a hard to say the proof. Hard result to prove. So, and use this, and the key result which is used here is step here. Okay. So what we basically, the key step is that you can think in the sense of lemma also, which is again hard. A perfect complex on U. So do you know that then the problem was when we can lift a perfect complex from U to X, and the point is that a perfect complex on U extends to a B prime in perfect of X if the class of P is 0 in K naught of U. So every perfect complex will have a class in K naught of U, and if its class vanishes, it should be able to lift. Because let's say prove that this is not true for vector bundles itself. And this is the main step, I guess, like Thompson points out that it's one of the very, very key steps that you cannot do it when you work with vector bundles only, but when you work with a complex of vector bundles and you use these quasi-isomorphisms, you invert quasi-isomorphisms, then actually you can do it. Is the statement clear and importance of it? Yeah. Okay, so this is one of the main interesting point why we go to perfect complexes. Why do we care about category of Boltzmann categories? Why you should learn about that and everything. Okay, so I will finish the proof here. I'm not going to say anything about this. Obviously, this is not complete proof, but yeah. So one has to prove this statement basically. It's enough to show and see how to use this lemma and how to prove this lemma. Okay, I want to discuss some applications in remaining 12 minutes or so. So obviously one can prove May victories. And the fact one has to use here. So May victories is same, right? X, U, and V is given to you. K theory of U union with V, mapping to K theory of U. Okay. Write this given U, V inside X, open. Okay. So then the only failure will happen on basically on the last step, K naught. This will not be surjective on the K naught. And so this statement still makes sense, which we proved for G theory. But now we are saying that it holds for K theory for any schemes, not for the rest of the schemes. And the main step is that so proof follows from. So this is a good exercise you guys should try. Follows from localization theorem. theory and the following and the following fact that following fact. So this is called excitation for K theory. Excitation. Let Z inside U is closed. This is open. Next, then K theory of X on Z. Derivative of U on X on Z is X. Okay. It says that when you're looking at the perfect complexity are supported on Z, you can take a small neighborhoods of Z. Okay, is lemma clear? So this is a closed immersion. This is the notation for closed immersion. This is notation for open immersion. And we are saying that excitation holds basically for that. And using this statement and localization theorem, you can prove this Maven theories. Again, it's a very interesting exercise. You guys should do that. Okay, so the second statement, which is interesting, second application. There are many more applications actually of this localization theorem for theory, but you can see that this. Okay, so it says that so for all Z in X closed, there exists an exact sequence. Yeah. So okay. So before adding this, let me ask you this question. So we saw that So in localization theorem, basically what was happening when we worked with K theory, this map was not surjective, right? The last map was not surjective. So which means that if we want to dream that we live in a very nicest world and everything should be fit into a long Z sequence, at least there should be something here. There should be some co-kernel should map to something, and which can be fill into a long Z sequence. And the way we are writing, it should be a negative K theory. So the question was how define it. So that was a challenge with these people. Like they knew that this map is not surjective, but what is its co-kernel? How to determine that? How to study that in some sense? And that's what we call as negative K theory. But how to define it? We cannot use this long Z sequence to define it because it's this co-kernel of this. We cannot define it with a negative K theory of this K naught of K minus 1 of X comma on by cannot be just co-kernel of this because then it will stop there. But more likely the way this localization this long sequence suggests is that there should be infinitely many negative K theories. It can happen. So what we want to do is that we want to study this negative K theory in some sense from a different point of view. So these applications actually help us in doing that. That's the motivation for this application. So this says that there is an exact sequence with the K theory of X on Z. Pull back. There are two projections. Basically, you take X cross A1, which I'm writing as X cross T, just because I want to emphasize on the variable, and ZT. And then there's another X comma A1 copy, which the variable I want to write T inverse. Yeah. And these two A1s basically have a G1 inside. I want to pull this two K theories back to that. This pullback exists because we are working with K theory anyhow. So this is J1 pullback, J2 pullback. Okay. So J1, J2 are just the immersion of GM in two copies of A1. Okay, so now this map is not surjective. Actually, the co-kernel comes from Kn minus 1 of X on. for every x for every n greater than. Okay. Is it okay? So this is the statement, and
Can you explain what is x adjoint t?
yes, this is x cross a1, where the a1 coordinate is writing as t. The x t, I think is sense of x cross z. Yeah. So I'm specifying the variable basically. It's x cross a1. You can abstractly the scheme x cross a1. Yeah, it's a1x. And similarly, this copy also is a1x. But point is like we want to see the variables as a different variables, especially t and t inverse, and then says that gm x sits inside that. A1 minus 0 x sits inside that. That's two copies. Is it okay?
Right.
Yeah. Okay. So let me not go into the proof of this. So okay, let me just write here, and interested people can see the proof. Follows from localization theorem. And what is this called? Projective bundle formula. So I have not got time to discuss this projective bundle formula, but this is also very interesting. This says that actually for P1, it says that it's actually isomorphic to the two copies of an X. It's isomorphic to two copies of X. And it gives you more how these isomorphism, how these things happen, and you use them to conclude this. Using the localization, now you can see that localization will apply maybe basically on this P1 of X with two copies of A1, right? You can see why is A1 of X. I want to write Z T and T inverse because they are open subschemes of P1 of X. Yeah, and then there's the intersection which I'm calling as Z T comma T inverse X plus G. Okay, so proof is you can do it. It's not a very hard proof. But the main thing which I want to like just say in last minutes is that when you take n equal to 0, so when I take n equal to 0, so up to this is this is actually exact when n is equal to 0. So this is exact when n is equal to 0. Right? So there is no, obviously this is not there, it is not defined. We have not defined k minus 1 of x on z, and the point was like we should be able to define it. And I'm saying that for higher ends, there's a long exact sequence, this 4 terms long exact sequence, 4 term exact sequence, which suggests that we should define k minus 1 as co-kernel of this map. And then prove that on between those k minus 1s, there's such a map also. And define k2 as a co-kernel of that, and so on and so forth, and prove, and then then there will be this kind of long exact sequence will always exist. And but then you have to prove that the localization, the long exact sequence you prove for localization is actually extended with the negative. Okay, I hope that I'm clear. I don't have time to write this all, but this is a motivation to define negative theory. This is a way to define a negative theory using this long exact sequence as a negative k groups basically, not k theory. I'm not defining it as a spectra right now. I'm just defining it as a negative k groups as a co-kernel of this map k minus 1, and then we'll construct a map J1 pullback, J2 pullback between k minus 1s, and then define k minus 2 as such, and so on and so forth. Okay, and that will fill my long exact sequence on the right hand side in the localization. Okay, I stop there. Any questions or comments?